Hello everyone, welcome to lecture 14 on Mechanics and Materials 1. This is our third lecture on the topic torsion. So we have 4 lectures in total on the topic torsion. In this lecture we cover sections 5.5 and 5.7 of the chapter 5 of the Hibbeler book. We essentially talk about 2 topics. We talk about statically indeterminate torque-loaded members, and we talk about torsion of thin-walled structures. And those 2 topics, they correspond to sections 5.5 and 5.7 respectively. So the first topic we want to talk about in this lecture is statically indeterminate torque-loaded members. And in order to address this topic, we should recall a similar topic that we had, but for axially loaded members. So for axially loaded members, we learned how to handle statically indeterminate axially loaded members. And these members usually are members that have too many constraints. And basically that means you have too many unknowns and too few equations. The good news is that if you have a statically indeterminate member, whether it is torque loaded or axially loaded, you can treat them similarly. So what you have learned before also is useful for now. So if you remember what we have done before, the process of dealing with such problems was composed of 2 steps. The first step was to draw the free body diagram and write equilibrium equations. And as we spoke before, usually doing this step, step 1, is not enough if you have a statically indeterminate structure. If you have a statically determined structure, of course this would be enough, and then you get n equations, n unknowns, and you can solve it. But if it is statically indeterminate, you need to also do a second step to come with enough equations to be able to solve the problem. Now, the second step is usually writing some sort of compatibility constraint. And these compatibility constraints, they are usually related to the geometry or geometrical feature of the structure. And we can, for instance, use the principle of superposition to deal with these problems. Okay, so long story short, if you have a statically indeterminate structure, you need to go through 2 steps. Step 1, free body diagram and equilibrium. Step 2, compatibility constraints. So again, before we talk about statically indeterminate torque-loaded members, let's recall what we have done with axially loaded members. So we want to remind ourselves how we dealt with axially loaded statically indeterminate bars and basically extend that idea to solve problems that are torque loaded. So the bar AB here, fixed at 2 ends A and B, it shows an axially loaded member that is also statically indeterminate because, as you can see, it's fixed on both ends. And that means you would have 2 unknowns. You would need to find the reactions from supports A and B. So these are 2 unknowns, but you would have 1 equation for this. So if you draw the free body diagram, indicating the forces from the supports A and B as FA and FB respectively, your equilibrium equation reads sum of forces in the x direction is 0, and that basically tells you that FA plus FB plus P is 0. That is your 1 equation that you have, but then again you have 2 unknowns, so we are looking for a second equation to solve this problem. Now, in order to find the second equation, we look at the system, then we decompose that system into two different systems. We decompose it to system 1, where you have only force P applied, and then we have system 2, where we have only force FB applied. And in all of these pictures and all of this problem, we assume that the plus direction is towards right. So this is our positive direction for force and displacement. Now, for system 1 and 2, you can calculate displacements separately. And then remember that the formula to relate displacement to load is delta equals PL over EA. And the compatibility constraint, the geometrical constraints that we talk about, is that you know that the bar is fixed at point B. So the displacement at point B, which is the sum of the two displacements from the system 1 and system 2, it must be 0. So this is exactly your second equation. So this is your second equation. This is your first equation. And from these two equations, now you can calculate both unknowns. What we want to do now is to take this view and extend it to a torque-loaded problem. So now exactly think about a similar problem like before. Now you have a shaft between points A and B, and assume that the shaft is fixed and at both supports A and B. And then on a point C somewhere in the middle, you apply a torque. So in the previous problem, we applied a force. Now you apply a torque. So we are dealing with a torque-loaded member instead of an axially loaded member. The first step is the same. We draw the free body diagram, and then assuming that from the supports A and B, you get the torques TA and TB respectively, you have your equilibrium equation, and then again, equilibrium equation in this case is essentially the sum of moments with respect to x-axis is 0, and then the moments with respect to x-axis is exactly the torques. And for simplicity, again, you can assume that this is sort of your plus direction for your moment. So if you assume that, the counterclockwise rotation would be your plus sign. Okay, so this is our first equation. But then again, we have two unknowns, so we are looking for a second equation. And similar to what we have done before, that second equation comes from some sort of compatibility. So now what we do is we take that member, we decompose that into two parts, part 1 and part 2. In part 1, you only apply T and you get no reaction from B. In part 2, you only apply TB and you have no external torque from point C. And then again, similar to what we had done before, we calculate phi B for system 1, that is the angle of twist for system 1, that is the angle of twist from system 2. And then you know that the sum of these two must be 0. So again, the sum is 0 because we know at point B is fixed. So angle of twist at B is 0 because it is fixed. Now for each of phi B1 and phi B2, we can use the formula that we had to relate the angle of twist to torque, that is phi equals TL over GJ. And that's what we want to do now. So for the first system, phi of point B, so the angle of twist for point B is the same as the angle of twist for point C, because between B and C, there is no additional torque. So torque between C and B is 0, so there is no change in angle of twist from C to B. So whatever angle of twist you get at C, you would get exactly the same also at B. So angle of twist at C is T times LAC, because angle of twist at C is basically angle of twist at C with respect to A, and because A is fixed, then that is the angle of twist at C. So that is T LAC divided by GJ. Now from the second system, from system 2, you can also calculate the angle of twist. So if it's a bar here, and then you have now torque B, angle of twist at point B from system 2 is TB, LAB, the total length, divided by GJ. So what we want to do is to impose that the sum of the angles of twist, so phi b1 and phi b2 is 0, because this is exactly phi b, and we know that it's fixed at point B. So if you add these, they should end up with 0. Inserting these equations into our relation here, it gives you the equation that we were looking for. So it's TLAC plus TBLAB equals 0. So this is your second equation. This was our first equation. Now we have two equations, two unknowns, and we can calculate the torques, and that's exactly what we are going to do here. So what we do here is that from this system, you can see that T is minus TB LAB divided by LAC. And then you insert that T into your first equation. So you end up with the yellow equation here. And then if you reorder these terms, you would have this relation. TALAC is equal TBLBC. Or you can say TA over TB equals LBC divided by LAC. So what does this mean? This means that if the arm from AC is longer than the arm from BC, then the torque you get at A is less than the torque you get at B. And also it means if the arms are equal, so if LBC and LAC are equal in length, then you get equal torques, which is very similar in nature to what we had again with axially loaded members. So if you look at the example that we just had at the beginning of this section, we showed this bar as an example, and then let's say you apply a torque of 500 Newton meter. Now in this picture, LAC is 3 meters, LCB is 2 meters, so that means you need a smaller torque TA compared to a torque TB. So TA LAC must be equals TB LBC. But also we know that the sum of the two must be minus 500, or the sum of the two plus 500 is 0. So if you look at all these equations together, you can clearly see that it basically means that TA must be minus 200 Newton meter and TB must be minus 300 Newton meter. And then again, minus, it simply shows that the directions that we had assumed here are not correct, which makes perfect sense because the torque you applied externally is, let's say, counterclockwise. So in order to cancel that, you would need torques that are clockwise. So that's why you get the minus. So that's basically it. This is how you handle statically indeterminate torque loaded members, and this is sort of the magic formula you should remember. But also more importantly, you should remember this was an example. So the procedure that we come to this point is much more important than just this message or than just this equation. You should always remember the procedure. The procedure is always writing the equilibrium equation, that is step one, and then writing the compatibility equation, that is step two. And then for different examples, these two conditions, they could change. For this example, it was exactly like this. We will have an exercise and we will have some more practice on that. Exercise 1 in this lecture is similar to problem 5.8 on page 220 of the book. The solid shaft shown in the figure has a diameter of 20 millimeter. So this is the shaft and it has a diameter of 20 millimeter. If it is subjected to the torques shown, determine the reactions at the fixed supports A and B. So you have two external torques applied to it. It is fixed at B and A, and you are asked to calculate the reactions from the supports. And this is also a statically indeterminate problem or statically indeterminate member under torque. So it relates exactly to what we just discussed about. So again, the first thing we want to do is to draw the free body diagram and write the equilibrium equation. And if you do that, assuming that you need a direction for your plus convention, so basically you need to say how you define the positive direction for your rotation, we take x as such. So we assume that x at 0 is at A, and then this is your x-axis, longitudinal axis. Now, with respect to that axis, if you think of a counterclockwise direction, this would be your plus direction. If this was the way that we decided the x should be. And now, based on that, we draw the torques. The external torques, 800 and 500, are here. And again, for the convention we have, this is like a plus 800, this is like a minus 500. Because this one is now clockwise, this is counterclockwise. We draw TB and TA as if they are plus, so they would follow a counterclockwise direction. Okay, so once we have this free body diagram, now we write the equilibrium equation for that. The equilibrium equation here is the sum of moments with respect to the x-axis is 0. And then again, because x-axis is chosen as such, we would have plus TB plus 800 minus 500 plus TA equals 0. So we have one equation, two unknowns. So what we want to do now is to find the additional equation through compatibility condition. So the compatibility condition here, or the geometrical constraint here, is that it's fixed at both ends. So what does that mean? That means point B with respect to point A does not rotate. So phi B with respect to A is 0. Now, phi B with respect to A is phi B with respect to C plus C with respect to D plus D with respect to A. So basically, you would add these three rotations to find how much rotation you get between A and B. Now, for each of them, we remember the formula we had for twist angle, that would be TL over GJ. The whole shaft is made from the same material, so it has always constant J and G. So it has the same shear modulus because it's made from the same material, and it has the same J because it has the same cross section. Okay, so G and J do not change. Now for part BC, the formula would be TBC, so that is now the internal torque from B to C. Remember the torques in this formula, they are now internal torques. So this would be the internal torque from B to C times the length of BC. Now if you cut the member somewhere here, you can imagine that the internal torque between B and C would be exactly the same as TB. From C to D, on the other hand, the internal torque would be TB plus 800. And then again, the way to see that is that you need to cut this member, and basically you can imagine that if now you have a shaft, you apply 800 here, you apply TB here, how much would be the internal torque to balance this? And if you look at this, you can see that it has to be TB plus 800. And then again, the sign convention follows from what we had discussed previously, so it's a plus. And then from D to A, so DA, you would get TB plus 800 minus 500, which is TB plus 300. So that is TDA, which by the way happens to be also exactly minus TA, which makes perfect sense because if when you cut this member from here, you can look at it, let's say from left, or you can look at it from right. If you look at it from right, then it makes perfect sense to see that you would need a torque that is minus TA to keep that member in equilibrium. So now you would be looking into a member which has TA on that end, and then here you have TDA. So now you can clearly see that TDA must be minus TA. But also you can see that by comparing this with our free body diagram equation. Okay, so if you insert these values now, you would have a relation which you did not have before. So this would be your second equation. This is equation 2, this is equation 1. You have two equations, two unknowns, and from these two equations, two unknown system, you can calculate the torque at B and the torque at A. The torque at B would be minus 645 Newton meter. At A, it's 345 Newton meter. And then again, minus here means that this direction is not correct, so it's the opposite. But for A, what we have is already correct, so that is the reactions. Okay, so that's how you can solve this problem. But what we did here, although it was very neat and simple to understand, it was not exactly the principle of superposition. So what we can do now is to also solve this alternatively using the principle of superposition, and that's what I want to do. In order to solve this problem using the principle of superposition, what you can do is to split the system into three systems. Remember, previously we had to split the system into only two systems, but now because we have three torques, we would split it into three systems. And then calculate the angle of twist at B for each of those systems. So that would be phi B1, phi B2, phi B3, corresponding to system 1, 2, and 3 respectively. And then we know that the sum of them, which is the angle of twist at B, or the rotation of B with respect to A, it is 0. So you can do this. Now, if we do that for system 1, the angle of twist at B would be exactly the same as the angle of twist at D, because between B and D you have no additional torque, so you have no additional change of angle of twist. And then again, using the formula TL over GJ, you can calculate that. But now the T that you have here is the internal T between D and A. And if you calculate that internal T again, remembering the way we did that, it would be minus 500. The length of AD is 0.3. And then again, we divide by Gj, but Gj is constant. Again, J is constant because the formula pi over 2c to the power of 4 is constant overall, and then it's all made from the same material. So that's for part 1. For part 2, we calculate phi c. So again, the angle of twist at C is the same as the angle of twist at B from system 2 because we don't have a change from B to C. And now the internal torque from A to C is 800, and that is a constant, so there is no change. And that's with a plus. So you do that, and then eventually you do it for the third system. For the third system now, phi B in the third system is TB LAB divided by GJ, and now LAB is the whole length 2 meters. And the torque, again, it's an internal torque, but in this case, it happens to be just TB itself. We have only one torque. Okay, so if you insert these values into this equation, then you end up with this equation. And this is your second equation, essentially. And using this equation and the equilibrium that we had, you can calculate the supports, and that's what we want to do now. So basically, if you reorder the terms in that equation, you would get this. So you can see it's one equation, one unknown, basically. You can calculate TB directly from this one, and you end up again with minus 645 Newton meter. Then you take this into this equation and you can calculate TA, which would also be now 345 Newton meter. All right, so this was a second way of computing the torques, the support reactions from A and B, but now we did it using the principle of superposition as an alternative approach. You can do it either way, and as I mentioned before, these are only examples. It's very important that you learn how we do this, because for different problems you need to be creative and you may need to come up with different compatibility equations. They are not always following exactly the same rule. So we will have another exercise on that and we will talk about that. But before that, let's look at what we did before again. So when you want to handle statically indeterminate torque loaded members, you should always look for two sets of equations. The first one is the set of equilibrium equations, and we combine that with free body diagram. And the second one is to look into compatibility equations. And usually, as I mentioned before, these are geometrical constraints. Now, although this problem looks slightly complicated, it's very, very similar to what you have done before in terms of combinations of springs. So if you find an analogy between combinations of springs and what we are doing here, I think this will help you to better understand the problem. So for instance, if you think of two springs that are combined in series here, your equilibrium equation is that the force in both springs is equal. So in spring 1 and 2, if the force is F1 and F2, the force that you apply at the end, so the external force is equal F1 is equal F2. That is your equilibrium equation. Now, what is the compatibility equation? The compatibility equation is that if you get a change of delta here, that delta would be the sum of delta 1 and delta 2. Okay, so delta here is the sum of both delta, but equilibrium gives you the equality of forces. Now, you should compare that with a combination of springs in parallel. If you have now this spring 1 and 2 in parallel, now your equilibrium equation, if you have a force F here, then from system 1 and 2, you get F1 and F2. So now your equilibrium equation is F equals F1 plus F2. Whereas your compatibility equation, it tells you that delta equals delta 1 equals delta 2. So the compatibility equation for springs in parallel is sort of similar to equilibrium equation for springs in series, and compatibility equation for springs in series is similar to equilibrium equations for springs in parallel. And as you can see, when you think of the problem in terms of springs, it's fairly simple to come up with this for each system, and this is exactly what we want to do. So the previous problem that we looked into, it was more similar to this problem, because if you remember, we started adding the angles, and by adding the angles we got a total angle, and then we had a constraint on that. So this is almost like the previous problem that we just looked at, but the next problem we want to look at is more like having springs in parallel. So the next problem we will be looking at is similar but also different from the previous problem. The second exercise in this lecture is similar to problem 5.9 on page 221 of the book. The shaft in the figure is made of a steel tube bonded to a brass core. If a torque of 250 Newton meter is applied at its end, plot the shear stress distribution along a radial line of its cross-sectional area. The shear modulus for steel is 80 gigapascal. The shear modulus for brass is 36 gigapascal. So basically you have this steel tube on the outside, and then you have brass, or the brass core on the inside. And also remember, steel is an alloy made from iron and carbon, and brass is another alloy made of copper and zinc. So we want to solve this problem, and again, if you compare this problem with the previous one, you can sort of see the similarities and differences. This is also a statically indeterminate problem, but as you can see, unlike the other problem that we had, it's not fixed at both ends. So it's only fixed at one end. So similar to the previous problems that we talked about, we need to look for two sets of equations. We need to look for equilibrium, and we need to look for compatibility. Now, equilibrium in this case would be similar to before, is the sum of moments with respect to x-axis is 0, and then assuming that this is your, let's say, x-axis, and this is your counterclockwise rotation as a plus, then from the tube and from the core, you get two torques. So if the torque you get from the tube is TST, and the torque you get from the brass core is TBR, then plus 250 minus TBR minus TST must be 0. And then again, pay attention that TBR and TST are now drawn different than what we usually do for the plus direction. So if we had them drawn like this, this would have been plus. But we assume that they are in the opposite direction, unlike what we did in the previous problem. So again, it doesn't matter how you draw them, it matters to be consistent though. So as long as your drawing is consistent with your signs, it's fine. So that's our equilibrium equation. Now, our compatibility equation here is that the angle phi, the twist angle, is equal in the steel tube and in the brass core. And you can imagine that by looking at this picture. So if you have a cross-sectional area, and if you turn a line by a certain angle, you can imagine that every radial line, it turns with the same angle. It doesn't matter if it is inside or outside. So the angle of twist is equal. Now the angle of twist for the steel tube is TST L divided by GST JST. And then again, remember, angle of twist is just following our common formula, phi equals TL over GJ. But now for each part, we need to use its own T, its own L, its own G, its own J. Because both parts have the same L, I'm just using the letter L, so LST and L brass are equal. But then the T is not the same, so you have TST and T brass. They have different G's, the shear modulus, which is given, and they have different J's. So we insert those values. The shear modulus of steel is 80 gigapascal, for brass is 36 gigapascal. J for steel, it's a steel tube with external radius 20 millimeter, internal radius 10 millimeters, as you can see here. So the J of steel would be pi over 2 CO to the power of 4 minus CI to the power of 4. And then for brass, it's just the core, it's a solid shaft. It's pi over 2 C to the power of 4. And now C for the brass is the external radius of the brass core, which is the internal radius of the steel tube. So it's 10 millimeters. They are perfectly bonded together, so that means the internal radius for the steel tube is the same as the external radius of the brass core. So if you insert that, now you have two equations, two unknowns. From the second equation, you find a relation between the torque in the steel part, in the steel tube, and the brass core. And then using that relation in the first one, you can calculate each of them separately. So that renders the torque in steel tube to be 242.7 Newton meter, and the torque in brass core 7.28 Newton meter. Okay, so we have the torques now, but this is not what we were asked to do. We were asked to draw the shear stress distribution. So everything we have here is what we had done before. Now, to draw the shear stress distribution, recall the formula that we had before to relate the shear stress to torque. So shear stress tau is equal TR over J, T being the torque, R radius, and J is polar moment of inertia. Now for the brass, you can imagine if R is 0, we are at the center, so shear modulus would be 0. But the maximum shear modulus, the maximum shear stress for brass is the torque times maximum radius of brass divided by J, the polar moment of inertia of brass, and that would be 4.63 megapascal. So in the brass core, you have a distribution which starts from 0 and goes all the way to 4.63 megapascal. Now on the tube, you have also a range of shear stress that goes from a minimum to maximum, and that is also linear because it follows exactly this relation. Now, the minimum Tau minimum would be T R min divided by J. So when you use the minimum radius, you get the minimum shear stress. When you use the maximum radius, you get the maximum shear stress. So for the tube, the minimum radius is not zero, unlike the core. For the tube, the minimum radius is 10 millimeters. So you insert that, you use the J, the polar moment of inertia for steel, you use the torque for steel as we have calculated before, and then you get the minimum shear stress for the steel tube, and that is 10.30 megapascal. Now, if you insert the maximum values, so the maximum radius for a steel tube is 20 millimeters, so 0.02. The torque is the same, J is the same, and for that you get the maximum shear stress for the steel part, and that would be 20.60 megapascal, which is 2 times 1030, and that makes sense because the outer radius is 2 times the inner radius. So if we clean this up and if we collect them, we can see that for the brass part, the maximum shear stress is 4.63. And then again, we are not writing it because it's trivial, but for the brass core, the minimum shear stress is 0. For the steel tube, the minimum shear stress is 10.30, the maximum is 2.60. Now, if you want to draw them, you can draw them like this. So basically, for the brass core, the shear stress starts from 0 to 4.63 or 64 here. And then in the tube, in the steel part, you would have a jump of shear stress to 10.3, which goes again linearly to 2.16. So you have a jump of shear stress where the material changes. But if you look at shear strain, you can see that the shear strain remains linear. So if you remember, shear strain follows the relation gamma equals R divided by C gamma max, indicating that shear strain is linearly proportional to radius. Okay? But shear stress is more than that. For shear stress, you need to also take into account the material itself. For shear strain, the material doesn't matter. It's just a linear distribution in R. And if you look at that, for shear strain, you get a continuous distribution. All right. So this was another interesting example dealing with statically indeterminate torque-loaded members. The second topic of this lecture is torsion of thin-walled tubes with closed cross-sections. So if you recall from one of our previous lectures, we discussed two shafts. One shaft with solid cross-section, so it's just a filled cross-section, let's say shaft B, and another shaft with the same weight, but now with a hollow cross-section or a tubular shaft. And if you recall, we concluded that for the same weight, shaft A carries more torque. And that can be explained by the formula that tau is TR over J. And if you fix tau to an allowable limit, then you can see that a larger J would give you more torque. And for the same weight, shaft A has a larger J compared to shaft B. Or otherwise, for the same J, shaft A is lighter than shaft B. Okay, so this simple example, it essentially motivates the idea of designing thin-walled shafts. And these are applicable to lightweight structures. A thin-walled shaft looks like this. So basically, you can have a shaft that is not necessarily circular, but it is thin-walled. And we want to learn how to calculate or how to design these shafts and what is the relation again, what between torque and, for instance, angle of twist or shear stress in these shafts. So we want to learn that so that we can design thin-walled shafts or thin-walled tubes. Similar to before, we need to make assumptions to make sure that we can calculate or we can compute the response of the shaft with good approximation. We make two assumptions. The first assumption is that we have a constant but arbitrary shaped closed cross section. So you have a cross section here. It has an arbitrary shape. It doesn't have to be circle or rectangle or triangle or anything. It has an arbitrary shape, but it is constant. So it's the same shape throughout the length x. The second assumption is that the thickness could vary on the wall. So the thickness T here, it may be less here, it may be more here, or more here. So the thickness could be different on different parts of the wall at a certain cross section, but it is constant with respect to x. So whatever thickness is here, it would be the same if you go in the x direction. So we assume that these two assumptions hold, and based on these two assumptions, then we can proceed. We also define a new concept, the concept of shear flow. So shear flow is the product of the average shear stress times thickness. So stress times thickness, it's a new quantity. We just call it shear flow. Let's call it Q, for instance, small letter q, and we will see why it's an important quantity. We can see it in this picture. So if you look at the picture here, assuming that this is a cutout of the shaft that we had in the previous picture. So again, if I show you this one, we just take this part that we are showing here. If you take that cutout and it has an arc length s, which otherwise could be ds if it is very small, but important is that in this direction it's dx in the length direction, and it has the thickness t. So if we enlarge that part in this picture, you can also show the shear stress distribution on that. So this is our dx, and this is that length or arc length s. And for that one, now if you write the equilibrium on two sides, for instance, if you look at this side here and this side corresponding to that, if you write the equilibrium for that, so these two sides, they should be in equilibrium, you know that dFA, so let's say the incremental force on the side A must be the same as incremental force on the side B. Now the force on side A is stress times area. Stress is shear stress tau A, and area is thickness times dx, so TA times dx. On part B, stress is tau B, and the area is thickness times dx. Dx from both sides, they cancel together. So you can see that tau ATA is equal tau BTB. And this is exactly stress times thickness. So you can see that for different cross sections, this value, this quantity, stress times thickness, remains constant. It's the same at every point, and that's why we basically pay particular attention to it, and we just define it as a quantity shear flow. Okay, so it's a constant value. It's stress times thickness. Now, also you can imagine that instead of showing the stress distribution or the shear stress distribution, you can assume that the stresses can be replaced by some sort of average shear stress, because we may or may not know the exact distribution of the shear stress, but also you can imagine that the distribution is possibly very uniform. So if you assume that the shear stress is almost uniform, you can replace it also by an average without loss of uh, generality. So again, now if you bring that concept to the definition of shear flow, then shear flow Q, now it would be toe average times thickness for any point. And obviously you can see that because Q is constant, you get the largest average of shear stress if your thickness is the smallest. So your smallest part gets the largest stress. And then again, this is the picture basically corresponding or to this one. And assuming that, again, uh, important difference between the two pictures is that because you assume that S is small enough, so you replace S by ds, then you can assume that the difference of thickness from this side to this side is also small, so you would talk about these toe averages. Okay, so this is basically the first concept that we need to talk about, and this is the concept of shear stress in thin-walled structures and shear flow. And what we want to do next is to calculate the torque. So the torque T, you can calculate it by the closed integral of distance times incremental force dF. So the distance is h from, let's say, the point O on the axis x. The distance h times dF, it gives you dt, that's moment or incremental torque. And if you integrate it over this closed surface, then you can get the torque. Now dF itself is toe average times dA, because toe average is dF divided by dA. And if you replace that, you see that torque is integral of h toe average dA, and then instead of dA you can write T ds, T being the thickness and ds is the, again, the length, the incremental length of that arc length, the incremental arc length. So you replace that and this would be your torque, is integral of h toe average T ds. And now you can see that, again, the product toe average times T, it appears by itself, and we know it's a constant. Okay, so we take it out of the integral, and you can come up with this one. So your torque would be then toe average times T, and the whole thing is constant, times integral of HDS. And now we want to know what is this integral. So the closed integral of HDS would be 2 times the integral of dAm, assuming that dAm is the area of this triangle, which makes perfect sense. So now h is height of that triangle, ds is sort of the base of that triangle. So HDS would have been the area of the rectangle that we have here. But you know the integral of the triangle is 1/2 of that. So the area of that triangle is 1/2 of h ds. And therefore HDS is 2 times dAm. And that integral of HDS is 2 times AM. Okay, so now we know what that is. That is the area AM, or mean area enclosed in that surface. So AM is enclosed within the boundary of the center line. And it's important that you pay attention that we are talking about the midline, the center line of the cross section. Okay, so we are talking again about the average, and we talk about the center line. All right, so now assuming that you know this is AM, and from the formula we had before, torque is 2 times toe average thickness times AM. Okay, and then again, you should maybe compare this with the formula that you had before. You had toe equals TR over J. So this was our common relation between torque and shear stress. Or otherwise, you could say torque is toe J divided by R. Now you get something like this. All right. So you can also, as I just mentioned before, you can reorder the relation that we had, and you would get this one. So tau is T divided by 2T AM. And as I mentioned, maybe you want to compare that by tau equals TR over J. So you can see that this denominator 2 times TAM is almost equivalent to J divided by R, which makes sense at least in terms of dimensions. So this is meter to the power of 3, which is the same as J divided by R. And also you can express that in terms of Q. So you know that Q would end up being T divided by 2AM. And now you can clearly see it's a constant because T is something you apply, AM is a constant. So this is your constant Q. This is your shear flow. Also, if you wanted to, you can calculate the angle of twist from energy method. We have not learned that yet, and we don't exactly calculate it, so I'm not showing you the proof here. But also for this type of cross section, if you wanted to, you can calculate the angle of twist. And then again, if you assume this is the formula for angle of twist for thin walled members, you can compare it with what we had before. So before, angle of twist phi was TL over GJ. Now you see TL divided by G. So basically what is left is something like 1 over J. This is sort of equivalent to 1 over J. So I think it's important that you can compare this to what we have done before. But possibly the most important relation for you is just to remember this, and remember that AM is the area enclosed by the, let's say, the midline on the surface. Exercise 3 and the last exercise of today's lecture is similar to problem 512 on page 232 of the book. The tube has a rectangular cross section as shown. So we have a tube here fixed at E with rectangular cross section and 2 torques applied on it. If it is subjected to the 2 torques shown, determine the average shear stress in the tube at points A and B. So points A and B are on 2 different walls, and we want to calculate the average shear stress on each of those walls. And as I mentioned before, the tube is fixed at E. The dimensions for the cross section are given here. Now, for the given dimensions, the first thing we want to do is to calculate the mean area, AM. So you can see the height is 60 millimeter, but you have the thickness of 3 millimeter on each side. So the height of the mean area would be 57 millimeter. So it's basically 60 minus 3 divided by 2 minus 3 divided by 2. Okay, so you get 3 divided by 2 reduced on each side. You do the same thing for the width. So it's 40, but then you need to subtract 2 times 2.5. So 40 minus 2.5 minus 2.5, that gives you 35. So the dimensions are 35 millimeters, 57 millimeters, and AM would be 0.002 meter squared. Now you use the formula that we had for the shear stress. Tau A, or average stress at point A, would be T divided by 2 times thickness times AM. The thickness where point A is 5 millimeter. The torque is the internal torque, and that internal torque is 35 Newton meter. So you can see that that should be 60 minus 25. So 35 Newton meter is the internal torque. Thickness is 0.005. You use this formula and then you calculate the shear stress, or the average shear stress at A to be 1.75 megapascal. Now you do the same thing for B. The formula is the same. It's torque divided by 2 times thickness AM, but now the thickness is 0.003 because point B is located on top of the member, and the thickness of that part is 3 millimeters. So if you do that, you calculate tau B equals 2.92 megapascal. That is it. That's what you were asked to calculate the shear stress, or the average shear stress at A and B. All right, so this was our third lecture on the topic torsion. We have 4 lectures in this series, so that means we have only 1 lecture more. In this lecture, we talked about sections 5.5 and 5.7 of the chapter 5 of the Hibbeler book. I'll catch you in the next one.